So the next thing I wanted to show you was VP21. So let me get my Google Colab session going. I use another browser for it, just for no terribly good reason, but I just prefer it this way. Sign into one of my Bloomin' accounts. Let's see. That one's fine. I have a ton of Google accounts. All right. There. And that's pretty good. Let me just get it more clearly placed on the board. I think that'll do. All right. So now I can put coding there. All right. So let's see what I want to do here. I want to play with ASCII, and this is really important. If you're not familiar with it, this is another essential thing like binary to learn. The way letters are encoded in computers and are encoded by ASCII, and the starts with unprintable characters like backspace and stuff, which are kind of confusing, but after you get above 31, it turns into normal things like spaces and asterisks and such, and the numbers are here, 0 through 9, and they start at 48 in base 10 and go to 57. And the letters start here with the capital letters. 65 is an A, and then they're in alphabetical order. And the lowercase letters are way over here at 97. So when your computer has any kind of text, it's just storing these numbers. Your computer, unfortunately, does not know the difference between different types of data. This is arguably a mistake, and there are some proposals to do what I wanted to do long ago, which is have more than 8 bits in a byte and have a few extra bits in each byte that record what type of data is stored there. And if we had that, we would not have memory corruption vulnerabilities, which are the most important type of vulnerability. I teach a lot of security courses where we exploit those and protect against those, because if there's a series of bytes in your computer, it doesn't know if it's executable code, an image, a text file, a music file. It doesn't know which of them they are, so you can easily confuse it. You can put something in for a password and then trick the computer into executing it as code. And that's how buffer overflows and all the memory corruption vulnerabilities happen. And they're still the most common vulnerability used to take over machines. Yeah? Is that a question? Maybe not. Okay, anyway, so we'll play with ASCII a bit. So let me start with some code here. Let's get to here. How to get to where I am? Yeah, you can find it there. Yeah, that's one way. Yeah, you also find it in this project. I put a copy of it in VP21, which you get by just scrolling down on the class page. Yeah, but that's fine. There's a bunch of them. Yeah, and it's a good thing to know. You don't have to memorize it, but you should be familiar enough with it to understand how to use it. And so let's take a look at it in Python. So here we are. I define a bytes object, which is capital ABC. Then I make a variable called A0, which is the first element in that byte array. And then I print them out with the type of data so we can see what they are. So let's see how this all looks. If I run that, it takes a few seconds to allocate a virtual machine to me, or a container, I imagine, with a certain amount of RAM and disk, and then it runs my Python environment. So here's ABC, that's bytes. It's a bytes object. The first element, A0, I printed the wrong thing here. Well, let's fix that. There. All right, so now I get 65. So that this is a bytes object containing 3 letters, which appear as readable letters, but if you look at one element, it's now an integer. And like I said, the integer 65 stands for a capital A. But there are different data types in Python, and as I've said before, and I'm sure I'll say a lot more, I spend most of my time in Python converting one data type to another. It's annoying, but that's the way it is. Then here I have a bytes. Now here, I added a D to it. So it changed into ABCD. But here I tried to change the existing second letter to D, and that failed. And this, you may remember from last time, this bytes object is immutable, which means you cannot change it. But you can add something to it because that creates a new object from the old one. It created a new object and then reassigned it to the same label. This, however, is changing part of an existing object, and that you're not allowed to do with a bytes object because it's immutable. All right, so that's a start. All right, and now we'll try byte arrays, which are the other kind of byte objects. So let me copy that, and let's just put it here. All right, so now I make the same object, a bytes object, and then I convert it to a byte array with the byte array, and then we'll play some games with that. So the first object is class bytes, the second is byte array, And now I can set the second thing to 68, which was 65 is A, B, C, D, C, I think. Oh, D, I guess, must have been. 65, yeah, 6, 7, 8, D. So now I changed the second letter to D, and it lets me do it because byte arrays are mutable. So I don't know why they do this to us. For all me, they should have had just one object, but they like making immutable things in Python. Yeah?
I'm trying to use the Google Colab thing.
Yeah.
But anytime I click the thing for new notebook in Drive,
Yeah.
it gives me an error saying I've already, there was an error loading this notebook. And it's saying that I've exceeded my drive storage quota.
Yes. Well, that means you got other stuff stored in your Google Drive. And so the simplest answer is just make a new Google account. That would be the best solution for that, because that must mean you have a ton of stuff stored, because they give you like at least 2 gigabytes, maybe more.
Yeah, they give you 15 gigabytes, but
Yeah.
about 12 of them are stored on my phone through pictures.
Yeah, and you're synchronizing, yeah, your Android phone is synchronizing to your Google Drive.
Yeah, so,
Yeah.
and if
And
I
you-
delete them from my drive, it deletes them off my phone.
Yeah, I would just make a different Google account. That's by far the easiest answer. That's a very good question. And the same applies. A lot of people have Google accounts with strange restrictions on them too, like from a company or a college. So making a fresh Google account is often the best way to get Google services. All right, and by the way, you don't have to use this environment. Let me just mention this for anybody that hasn't noticed it yet. You can use any Python environment you want, and in the projects, I have projects for at least 3 of them. You can install it locally. You can put a Jupyter Notebook on your local machine, which is what we're using here, or you can use the Google environment. And if you have another Python environment, that's fine too. Yeah?
I was just going to ask, with like Visual Studio Code?
Yeah. Oh, sure. Yeah, if you got that set up, feel free to use it. Yeah, and in fact, if you want to do some of the extra credit projects, you'll need it. Like down here for GitHub Copilot, you need Visual Studio Code. And feel free to set up any of these AI environments. The Google Colab gives you some AI code generation anyway. It's going to be the standard. We should all get used to having AIs help us. All right, anyway, so this is good. All right, so that's byte arrays. And let me get to the project here. Okay, so now unprintable characters are interesting. And actually quite a few interesting things about the way characters are stored. We won't be getting into all of it here, but all right. So now I make an empty byte array, or an empty bytes object, I should say. It's not a byte array, it's a bytes object when you have B followed by quotes. Now from range 65 to 70, I'm going to convert the integer to bytes, which is what this function does. And it's, I don't remember what the parameters mean. This is big endian, and I can't remember what the one is. In fact, maybe I'll find out. Now, the AI can sometimes tell me things, but in this case, it's not telling me, so I'm going to do this. Python 2 bytes. All right. And tell me what 2 bytes does. I've forgotten. Let's find out. All right, so 2 bytes. All right, this is annoying. 2 bytes. Yeah, that's why official documentation is usually to, okay, length and byte. Oh, okay, I want 1 byte. I'm going to give it an integer. I want it to be only 1 byte, so that integer must be between 0 and 255, and I want it big endian, which is means the largest number is on the left. But for 1 byte, it doesn't even matter. All right, that's what it is. Good. All right, so that's what I do. This will convert it to bytes, and therefore I can add that number to my bytes array. So I'm going to add 65 through 70, and then print out the result. Let's start with that. And there you see it as A, B, C, D, E, because I started at 65 and I printed 5 letters. So this is how you can take integers and put them in a bytes object. I might as well mention in older languages like Python 2 and C, none of this is necessary because all strings are byte arrays. And I always assume 1 byte goes to 1 character, and this turned out to be a really, really, really bad idea. The simple problem is you're stuck in English. If you want to write Chinese or Arabic or something, you're hosed because you've used up all the characters just for a small character set. But the really, really deep problem is the one I mentioned before. This is why buffer overflow exploits work, because strings are just a series of bytes. And I can put code in. I can put unprintable code, executable code in as if it was strings, and it'll take it. And in modern languages like Python 3, strings are lists of characters, and each character is a Unicode object. It can be from 1 to 4 bytes long, and it's completely different than byte arrays. And this was very hard for me to learn because I'd spent 30 years programming in C and other languages where a byte is a character. And in Python 3, they correctly understand that a character is a completely different thing than a byte. A character is a printed letter in some language, and that is not equal to a byte, not simply connected to a byte, and shouldn't be equated. So there I agree with them. They're quite correct to keep those things separate. So anyway, so I end up with a byte array here. Now I go from 5 to 10 and add that, and now I get this. So here, this is important to understand, and it could be real confusing in Python. These are both bytes objects. This one here printed readable characters. This one here printed unprintable characters. So each character turns into 4 characters, \x, and then 2 characters in hexadecimal. That's what it is. So 05, 06, 07, 08. And notice the last one was 10, and that turned into \t. So this is confusing at first, but this is the cruel thing. Printable characters print as the character. Unprintable characters print as the hex code, except for a few exceptions that are so important they have a special representation. \t is tab, \r is carriage return, \n is new line. So that can be pretty darn confusing. These are each objects 5 bytes long, even though they look very different. And if you mix the two, by the way, if I go down here and do another one of these, I add some let's put in, let's say I equals 65. That'll do it. And then print it again. All right. You'll get a mixture. So it's \x05. This is 1 byte. This is 1 byte, \x0a. This is 1 byte, \t. And this is 1 byte, a. So that's good and confusing when you print out byte arrays. It's a thing you have to get used to, but this is how you literally refer to unprintable characters by number. All right. All right, so now let's do some encryption. I do an awful lot of security and an awful lot of cryptography, so a lot of my projects are about that. That's what I naturally think of. So here's military-grade encryption from 2,500 years ago, the Caesar cipher. So I make a byte array, which is hello. Now I'm going to shift each letter forward by 3 letters in the alphabet. So I make a new thing called ciphertext, and this is the cryptography terminology. Plain text is the message you can read. Ciphertext is the scrambled message, which nobody should be able to read unless they have a secret key. That's the way it works. So to make the ciphertext, all I do is I take the, for C in plain text, that's going to be a byte removed from here. And in fact, let's print here C and type of C so we can see what it looks like. All right, and I'm just going to run this, and we'll just go down and look at, all right, so here it is. So C is an integer, 72, 69, and so on. So just like, so when you go into a bytes object with a for loop, it picks out the individual elements, and now they're integers. That's not obvious to me, but that's what happens. They're integers. I'm going to comment out that line so it doesn't get in the way, and this is common technique. Now, what it's going to do, it's going to take the integer, add the shift of 3, and then turn it into bytes. And then we're just going to print the resulting ciphertext. So, hello, H-E-L-L-O, turned into K-H-O-O-R, because the H, I-J-K, and the L-L-M-N-O, it just moved every letter forward 3 characters in the alphabet. This is the Caesar cipher, the classic Caesar cipher. And 2,500 years ago, when most people could not read at all, even a small scrambling of letters was like this enough to create military-grade encryption. Most people couldn't read at all, and a little bit of scrambling is enough. Nowadays, it's used for children's cartoons in the Sunday paper and toys inside lunchboxes and stuff. It was also used in the Civil War by the Confederates, who lost, you may remember. But anyway, although probably not because their cryptography was so bad. But anyway, so we can decrypt it. It's going to be a simple object, so let's try that. Okay, I give it the ciphertext, the one we just created, which is going to decrypt to hello. I'm going to shift by 3, and so all you do is take each element of the bytes object, turn it into an integer, subtract 3, turn it back into bytes, and then print it out. And so now that'll turn it back into hello. So you can encrypt and decrypt with those two routines in this very simple cryptography system. All right. Now, often you have a long string of hex characters. Real cryptography, modern cryptography, does not turn letters into letters. It turns messages of any kind into arbitrary binary objects. So modern ciphertext looks like this, just a long series of hexadecimal codes. So we ought to learn how to handle them. That's how modern systems like AES and RSA and all the classic cryptography algorithms that we're using to encrypt all the data on the internet these days works. So let me get to the right browser. All right. So this is a hex string. That's just a string. Without starting with a B, it's just a series of letters. 4, 8, 6, 5, 6C. Those are just treated as characters. And then here's the input, which is the hex string, and you'll see what it is. Here's how you make the bytes version. Bytes from hex. And as we're going to talk about in a couple classes in great detail, in hexadecimal, you use the letters 0 through 9, or the characters 0 through 9, and the letters A through F. So there are a total of 16 characters, and 2 characters in base 16 represent a byte. That'll encode any number from 0 to 255. So that's the most handy way to encode a byte. So this program here's the input, and that is a string. But we turn it into bytes, and it turns into hello. 48 is the ASCII for a capital H. 65 is for 65 in hex is for a small e. If it was base 10, it would be a capital A, but 65 in hex is a bigger number. 96 plus 5, 101. So that's coding out this hello with a capital H and small letters in bytes. And so here we have converting from bytes to hex. Here I put in Waldo, and I convert it to hex, which you do here, bytes version dot hex. Right, so this is the bytes version, is the name of the variable, and you put a dot hex on the end. By the way, you might have noticed something which I find very irritating about Python. Some things you do, and you put the active ingredient all different places. Here I had an object called hex string. So I had to write this function, bytes.fromHex, and I put the variable in here. Down here, I put the variable on the left and then put a dot hex on the right. Now, people that understand Python better than me might understand why you put the function on the right sometimes and you put the function on the left other times. I've never gotten it straight. I just have to keep looking it up at Google or the AI help or something to get it right. It's pretty annoying. In the languages I learned, more primitive languages, there'd be just one way to call a function and that's it. In C, the name is always on the left. In Python, it's sometimes on the left and sometimes on the right. And you people that are good at object-oriented code might understand why better than me. Anyway, I just mention it as in one of the irritations of Python. There are, by the way, many ways to do everything in Python. There are usually several different libraries you can import to do it. Anyway, these are what I found is the simplest ways to do it. So now I can convert hex strings to bytes, and I can convert bytes to hex strings. And you're going to need to do both of those things for a whole lot of applications, like cryptography and many other applications like manipulating images and such. All right. And all right. So now you got some challenges, which I'm not going to demonstrate. Let's talk about it. So here's hex string. You just have to convert that to readable text, and you've seen how to do that. Let me turn off the noise on this phone. These people that are calling me will have to call me later. All right. All right. Anyway, then there's a Caesar cipher, and then there's a better Caesar cipher, because the Caesar cipher I had just moved everything forward in the alphabet, so a Z is going to move off the end and turn into something goofy like a punctuation mark. So you have to fix that to decrypt this stuff. And here's the kind of thing, what I mentioned you can do with bytes object. These are hex strings. So if you turn them into bytes objects and add them together, you will make a message. So you have to compare, add 0E to 46, add 14 to 54, byte by byte to construct a message. And that's the kind of manipulation you have to do a lot of. There are so many applications for this. This is how you recover data, evidence. I'm teaching forensics class, I've been doing it for years. If you delete data on a hard drive, you lose the file name and the metadata, but the data is still on the hard drive, and you just have a string of bytes, and you have to find the getting an end of a file by recognizing characteristic flags in the bytes. This is called file carving. and it's the kind of thing you do. So that's why I say it's worth learning binary, because all kinds of cool things you want to do, like hack into systems, defend systems, analyze network traffic, analyze data you find on storage devices for evidence for a crime scene, all these things rely on you learning how to read hex and how to manipulate hex. Yeah?
So you're saying, did you say like you delete the photo from Apple iCloud, there is no way to recover it unless you paid for it, right?
Well, that's actually a very interesting question. Now, if you delete a photo from your phone, phones are not magnetic hard drives, they're SSDs, and most phones have a background garbage collection. I did this at DEF CON, in fact. You can delete it and you can watch it vanish. 15 seconds after you delete it, it gets erased by a background process. So it's pretty much gone on a phone. But if it's stored in a cloud service like iCloud, then the cops can get it by submitting a subpoena to iCloud. And I'm not sure about iCloud, but I know for Dropbox, they not only have all your stuff, but they have 30 days of old versions of all your stuff. So it's wonderful for cops. You can like destroy your phone with a hammer, and all they have to do is go to the Dropbox and find all your stuff.
Oh wow. Is it the same thing with MacBooks and iPads, same thing? If you delete
Yes, anything with an SSD. Although if you replace the SSD with a different brand, you may not be doing the garbage collection. It might be working like a hard drive.
Can you overwrite the data? Did you say like you fill up the gigabytes?
That the right way to erase it is indeed to overwrite the data, but that is in fact much more difficult than you might think, and it's in fact impossible on modern hard drives, because if you buy a terabyte hard drive, they give you like 1.05 terabytes. There's extra storage they don't tell you about, because as the blocks fail, it silently replaces them with the good blocks that are extras, and now you can never reach the ones that failed, not even to erase them. And the fact that they failed just means there was a read error in some of the bits. Most of the data is still there. So this is why companies never donate hard drives, and the police won't give them back to you. When the police have auctions, they'll have a whole pallet of things, and they will sell you machines, but there's never any hard drives in there, because there is no way to erase them that really gets all the data except to grind them up in a wood chipper. And this is why every company physically destroys magnetic media, storage media, because there's no way to really be sure you got the data off of there. Yeah?
I wasn't entirely sure, but isn't there like certain hard drives where with certain magnetisms it just erases the drive like completely?
Yes, you can try to erase it with a powerful magnet. The problem is there is no way to verify that it worked. And you never know. There's also a fundamental firmware erase command that is supposed to absolutely erase it, but again, there is no way to verify that it works. And my people in the business say it frequently does fail and people don't know. So there's a lot of blog posts. If you just buy used computers anywhere on eBay or something, you'll often find tons of old data left on there. Many people don't understand this, and they keep making this mistake. And by the way, Amazon made this mistake. When they first brought out Amazon cloud machines, they would give you a cloud drive without wiping the previous person's data off it. So all you had to do is run a forensic tool and you'd find the previous person's data on it. When they got embarrassed for that, they were forced to knock it off. But this is a mistake people keep making over and over and over. In fact, a district attorney took my forensics course because he had made this mistake. He had posted a public filing without realizing there was confidential data in it, which has happened many times, that data is exposed that way. It's data remnants is actually a huge problem in computing. The devices you use have leftover data on it, and when you dispose of them, people often don't understand how to clean them. Anyway, let me stop this recording. That was enough for that one.